Hello, this is FlippedHarber for Physics. In this video we'll go over the practice problems on page 174, numbers 1 through 5. Number 1, it says, if Ganymede, one of Jupiter's moons, has an orbital period of 7.15 days, how many units are there in its orbital radius? Use the information given in example 1. So the example 1 problem talks about how when Galileo looked at Jupiter's moons, he used the width of Jupiter as a unit of measure because he's looking out there. He can't really tell how big Jupiter is, but he can use it as a constant in order to measure things around it. So that's going to be our quote-unquote unit. Now it doesn't matter what your unit is in these problems because we're always going to be scaling, a practice in physics that we use when we really don't know quite what the units are for something, or we don't quite know what a measurement is, but we can compare it to something else. So we're going to use this equation that comes to us from Kepler's that compares orbital periods, those t's that you see on the screen, with orbital radii, the r's. Now, I've gone ahead and highlighted what we're solving for, r sub g, that is the orbital radius for Ganymede, in red. And I want to go ahead and give you a tip. When you're using this equation, always make sure that what you're solving for is on the top of one of those fractions. Don't make your life harder by putting r sub g on the bottom of the fraction, because then you're going to have to, like cross multiply or flip the fractions or whatever. Just start with what you're solving on top. It doesn't matter which one's bigger or which one's smaller, because if we have the bigger number on top on one side, it's also going to be on top on the other side. Alright, so let's get to starting this problem, and I want to go ahead and solve for r sub g. So I multiply r sub I, that is the orbital radius for Io, another moon that orbits Jupiter, over to the other side. So I've got a statement for rg cubed, and then obviously to solve for rg I have to make sure I take the cubed root. Now plugging in everything, we know that the orbital radius for Io was 4.2 of these units. How big's the unit? It doesn't matter because that's going to be our unit for r sub g also. Now our orbital period for Ganymede is 7.15 days. The orbital period for Io is 1.8 days. So we plug everything in, we plug it into our calculator, or if you were Galileo back doing this, you'd do it by hand or use an abacus or something like that, and you get 10.5 units. So that means that Ganymede is a little more than twice as far away from Jupiter as Io is. Okay, so let's move on to the next problem. In number 2, an asteroid revolves around the Sun with a mean orbital radius twice that of the Earth. What's the Earth's radius? It's not going to matter in this problem. We're going to compare back to the Earth's radius, orbital radius, so we don't actually need to know it. It says predict the period of the asteroid in Earth years. Okay, so that's great. I make sure that I have the asteroid on top on both sides of my equation. I've gone ahead and put what I'm solving for in red again. And I go ahead and multiply that t sub e, the orbital period for Earth squared, over to the other side. And I plug in. Now again, I'm scaling, so I'm using the orbital radius of the Earth as 1, which means that the orbital radius for the asteroid is twice that, it's 2. We just plug in 1 year because we're interested in finding the period of the asteroid in Earth years, so t sub e is just 1 year. Easy peasy lemon squeezy. Now, we cube one side, and we cube the 2 on one side. The ones don't really do anything for us, but then we've got to take the square root, so we find out that it's 2.83 years. It's going to take 2.83 Earth years for this asteroid to orbit the Earth. Now, number 3, from table 7.1 on page 173, you can find out on average Mars is 1.52 times as far from the Sun as Earth is. So an orbit and a half, if you want to. Predict the time required for Mars to orbit the Sun in Earth days. So again, we're going to go back to this equation. Now, it's really safe to use this equation when the two objects are orbiting the same central object. So Mars and Earth both orbit the Sun. So this is a great way to do this. If we're talking about Mars and the Moon, this is not cool to do because Mars orbits the Sun, the Moon orbits the Earth. So not cool to do if they don't orbit the same object. So moving things around like we've done in previous problems already, I'm going to solve for the orbital period for Mars. And again, I just plug in the appropriate number for the orbital period for the Earth. Since they want us to predict the time required for Mars to orbit the Sun in Earth days, I plug 365.25 in for the orbital period for the Earth. Plug it all into my calculator, making sure that I take the square root when I'm all done. I've got 684.47 days. So 684 of our days is how long the Mars year is. All right, last one. It says that the Moon has a period of 27.3 days, so not quite a month, and a mean distance of 3.90 times 10 to the 5th kilometers from the center of the Earth. Now, whenever we talk about orbital radius, we want to make sure that we talk center to center. So that's a nice number to use. Part A says use Kepler's law to find the period of the satellite. Okay, we can do that. We're just going to use that equation again. And then B, how far from the Earth's surface is that satellite? So once we find the period of the satellite, we need to go back and take this distance of 3.90 times 10 to the 5th kilometers and basically subtract off the radius of the Earth from that number to see how high up in the sky it is. Okay, so let's take care of this part A. We're going to solve for T sub s, that is the orbital period for the satellite. We're going to move that T sub m squared over. We're going to plug in 27.3 days. We'll plug in the appropriate numbers for the orbital radii, the orbital radius of the satellite, the orbital radius of the Moon, and we find out that the orbital period for that satellite, that should say T sub s, not T sub m, oh well, I'm not going to change it now, is 0.06 days, which is 88.5 minutes. Now, that's not that long. 88.5 minutes is not a long time at all. So let's see how high this object is. Again, we're just going to take the orbital radius that they give us for the satellite, 6.7 times 10 to the 3rd kilometers, and subtract off the radius of the Earth. So when we do that, we see that the height of this object is only 320 meters. That's not high at all. That's about the height of the Eiffel Tower in Paris. Nothing orbits that low. It'd be running into mountains and buildings all over the place. But if something did orbit that low, it would do that orbit in a little over 88 minutes. So the closer you are to the object that you're orbiting, the faster it has to go, the less time that it's going to have to get around there. Okay, so, we got one more. Sorry, using data from the previous problem for the period of the revolution of the Moon, predict what the mean distance for the Earth's center would be for an artificial satellite that has a period of exactly 1 day. So again, we're going to use some info on the Moon because it orbits the Earth to predict the orbital radius for an artificial satellite that has to orbit the Earth in exactly 1 day. So we shuffle some things around, we plug in, and we find out that that orbital radius is 4.30 times 10 to the 1st kilometers away from, excuse me, that's the orbital radius. So that's not the distance above the Earth, that's the orbital radius. Now why is this important? Well, if something has a period of exactly 1 day, that means that it's in a geosynchronous orbit. Now that's important to us because communication satellites are in geosynchronous orbit so that we don't have to move our satellites every time we want to watch TV or listen to the radio or stuff like that. We want to be able to aim our satellite dishes at those satellites and always be receiving information from them, or if you're one of the TV channels, you're sending information to those satellites. So all of our communication satellites are this same distance, this same orbital distance. That's a whole lot of room though. These things are not in danger of bumping into each other or anything. Alright, so now we're done. Time for you to give a shot to some of these problems on your own. I'll see you in class and I'll see you online.